I'm Engineer Joshua C. Agar. So in this video, you can see winds howling as Typhoon Ambo, international name Vongfong, was making its landfall on Summer Island. That's strong. People are finding it hard to walk across the wind. People are scampering for safety. Roof sheets are being blown away. Or even unfortunate for the since some of the buildings were notably had their entire roof structure completely blown away, which is strange since our design code specifically said that the design wind speeds for that area should be around 320 kilometers per hour, which is a lesson that we learned from Typhoon Yolanda, on which our LGUs are now comparing the storm Ambo to. So, is really Typhoon Ambo strong as Typhoon Yolanda? I'll be here to explain to you about that. Here is the satellite picture of Typhoon Ambo making landfall at 12 noon. This was taken from satellite Himawari. This was processed by the National Institute of Informatics in Japan. Made landfall on that strip of land which was occupied by the towns Dolores, Arteche, and Oras. And here, this is the place where Typhoon Ambo made landfall. It traversed west-northwest, passing through the northern edge of Calbayog, making landfall on the province of Masbate, then to Quezon, twice on Quezon, and it's now currently on the Cordilleras, where it's expected that it would be dissipating soon. There's a reason why I'm highlighting this. PAGASA's in order to know how strong Typhoon Ambo really is, of course we have to rely on actual site data. Someone recorded the wind speeds along Typhoon Ambo's path, then it would be beneficial for us into giving the answer. Unfortunately, the path that Typhoon Ambo passed has no synoptic stations or has no reliable surface measurement devices. In justifying that answer, try to look at this website, and this gives the live stream, the feed of data coming from some of the automated weather stations installed by PAGASA around the country. So if we're to look Samar, there are only 2 stations, namely Giwan Automated Weather Station and Katarman Automated Weather Station. Looking back, this is where Katarman is, and this is where Giwan is. A little bit far from where Typhoon Ambo had passed. In that shortcoming, I look into some of the automated weather stations from another agency from the DOST, which is the Advanced Sciences and Technology Institute, or ASTI. ASTI also installed many automated weather stations around our archipelago. They're classified mainly into 4, but I'll only name 2. The automated rain stations. Those stations record rainfall or precipitation and pressure. Sample of a automated rain station is the one in Calbayog City. So that's the one that I highlighted in this map. Meanwhile, there's an automated weather station that records the following: air humidity, air pressure, air temperature, precipitation, prevalent wind, maximum wind, direction of the maximum wind, and the average wind speed. It's the average wind speed, and this is the maximum wind speed. So if we look into those data, Typhoon Ambo made landfall on the 14th of May. So around 4:30, recorded peak winds of 38 meters per second. So if you're to convert, 136 kilometers per hour. Even though Typhoon Ambo passed over here, Catbalogan already was recording that high of wind speed. how much stronger are the winds if we were to move closer to the center of the storm. So in doing that, I need first to map the pressure field of the typhoon. The reason why I'm trying to map the pressure field is because the pressure isobars, or the difference pressure gradient, is one of the main driving mechanisms in the generation of the winds of a typhoon. So if I were to determine the pressure gradient, then most likely I would be able to estimate the wind speeds generated by that storm. So if I were to determine the pressure gradient, I need first to fit an analytical equation or an empirical equation, so that I'll just take the first derivative with respect to the r in cylindrical coordinates, then I'll be getting my wind speed. Post processing the pressure, I use the following from Catbalogan Station and from Calbayog Station. So here I am on my Excel worksheet. So these are the pressure from Calbayog Station. These are the pressure coming from Catbalogan Station. These are the wind speed peak gas recorded by Catbalogan Station. And following above are the locations of those stations in easting and northing. Cells D and E represent the easting and northing of Catbalogan Station. So these are the pressure. Next is I'll be correlating those points from the location of the storm over time, so that I can determine how far is the station from the center of the storm this time, at this time. In doing so, I took those coordinates to this website, and that website converted that to easting and northing. So I just copied and paste. That's the JMA data, which is post-processed also by the National Institute of Informatics. These were in latitude and longitude, so I have to convert them also to easting and northing. Now that I determined the location of the storm over time, which this is the location of the storm in easting and northing at 1800. These were in UTC, so if you're to convert 1800 to our standard time, it's 6 in the evening. So at 6 in the evening, these are the coordinates of the storm, whilst this is the coordinate of the station remains constant. Obviously, it's not moving over time. With that, I determined the distance of those stations from the center of the storm over time. So I use this formula. Then if I were to correlate the following, these are the pressure from Calbayog Station, and this is the distance of Calbayog Station from the center of the storm over time. Finally have my pressure versus distance versus pressure. Now I only have to fit some lines, some trends, or some models, some empirical equations in determining my pressure profile. So I used the pressure profile proposed by Holland in 1980, where further simplifies the hyperbolic equation, saying that values, the two constants A and B are somehow related. So it eliminates the solution for A. You have only to solve for B. And further details will be given at a later lecture when I finally discuss about typhoon modeling. So I assume 3 cases. First case, I assume that forecast data, what PAGASA JMA has forecasted regarding the minimum central pressure of the storm, the pressure at the eye is the same as the model. So this is the first case, 965 millibars. I only solve for Vmax, the maximum wind speeds, the location of the maximum wind speeds with respect of the center of the storm, the pressure at the outermost edges of the storm, those following 3 values. Second case, I have to solve for all of those values, the maximum winds, pressure at the outer edge of the storm, minimum central pressure, and the location of the maximum winds with respect to the center of the storm. The third case, I presume that what PAGASA has forecasted about Typhoon Ambo's intensity is correct. I inputted it's around 85 knots. So I have only to solve for pressure at the outer edge of the storm, the minimum central pressure, and the location of the maximum winds with respect to the center of the storm. And here are the results here in chart 1. So the orange trend line is case 1, the gray trend line is case 2, the yellow trend line is case 3. The blue values, those blue dots, are the actual data from Calbayo. So this is distance from the center, and this is the pressure. So now with comparing those three, I also evaluated the R squared values, the goodness of fit. Almost all of those trend lines are almost good as fit. High R squared value. There's close competition between case number 2 and case number 3, where R squared value of case number 2 is 0.99017. R squared value of case number 3 is 0.99014. We next have to rely on what Holland has prescribed regarding the B value. So here are the V value. B and B. They only prescribe a range on which the model is probable for a tropical cyclone. The value should be greater than 1. So we have 2 contenders, but we have also to consider that it is impossible for a storm to achieve 950. It's only a category number 3 typhoon according to the Saffir-Simpson hurricane scale. It's impossible for those type of storms to reach 950. They reach 950, 940, then they would be category number 4, which was not the case. So it's more likely that case 2 wins. Case 2 is probably the representative of Typhoon Ambo. So if we're to evaluate, it says that the maximum wind speeds is 38.72 meters per second. Converting that to kilometers per hour would be 139.49. I presume that this is the regional winds, which I also assume to be 10-minute sustained winds. So converting that to 3-second gas, I considered different types of exposures from at sea to inland. When considering at sea conditions, I considered gas factors to be about, I assume that the gas factors are about 1.2. If I were to assume inland, I considered gas factors to be about 1.66. Then I also took consideration of the shielding that may have happened, especially in an urban setting or a clustered on a population of buildings, if that area has many buildings. So one building shielding the other from the full brunt of the winds. I also took consideration of that. While taking note of that, peak gas that those areas may have experienced would be about 100 kilometers per hour up to 231 kilometers per hour. Still less than what's prescribed on our building code. So if engineers were to follow the building code, then it would withstand Typhoon Ambo. But given that many of those buildings suffered considerable damage, maybe should be checking whether they are properly designed. So maybe that's all for now. Thank you very much. I'm sorry for the incoherence of my words. This is my first time delivering a lecture about this, and I was a bit spontaneous about my speech or my wordings. So best regards to every one of you. I hope you've learned a lot today. Thank you very much.